Now the next topic, that is magnetism and Gauss's law. Okay. Now we already studied about the Gauss's law for electrostatics. Okay. And in that we discussed this thing, the electric flux associated with any closed surface, that is integration E dot dA, that is equal to the ratio of net charge enclosed by the Gaussian surface to epsilon 0. This Gauss's law we already discussed for electrostatics. Now we have to discuss Gauss's law for magnetism. So Gauss's law for magnetism says this thing: the net magnetic flux through any closed surface, that is 0. So mathematically, how one can represent this one? Say, suppose we have the magnetic field as shown in the figure, and in this particular magnetic field, we consider a closed surface. Now we want to find the total flux passing through this particular closed surface. So for that, consider any infinitesimal small ith surface element for which the area vector, that is delta Si, and the magnetic field at that surface element, that is Bi. Then we can write the flux passing through this particular ith surface element, that is Bi dot delta Si. Okay. So if we want to find the total flux passing through this entire surface, then we have to divide the entire surface into this type of so many infinitesimal small surface elements. Then due to each one, we have to calculate the flux passing through it. Then we have to take the summation of all those. Then we will get the resultant one. Okay. Now, so resultant flux, or we can say net flux passing through the given closed surface, that is sigma I equal to 1 to n phi I. This is the summation of the flux passing through all the infinitesimal small elements. So we can write sigma I equal to 1 to n Bi dot delta Si. Now here if we take limit delta S tends to 0, then the summation can be represented with the help of integration. So we can say the net flux passing through the given closed surface, that is given by integration B dot ds. Clear up to this? Now as per Gauss's law, the net magnetic flux through any closed surface, that is 0. So we can say this net flux integration B dot ds over the given closed surface, that is equal to 0. So this is the Gauss's law for magnetism. Clear? Now see, for electrostatics, we write the Gauss's law, that is integration E dot ds over the closed surface, that is sigma q upon epsilon 0. Now, exactly like this one, if we write the Gauss's law for magnetism, then integration B dot ds over the closed surface, that is the magnetic flux through any closed surface, that is equal to, now constant of magnetics, so that is mu 0. So here 1 upon epsilon 0, here the constant is mu 0. Sigma q, that is the algebraic summation of the electric charges. So here sigma qm, that is the algebraic summation of magnetic charges. But see here, as per Gauss's law, this magnetic flux through any closed surface, that is 0. So here, if we take this flux that is equal to 0, means mu 0 sigma qm, that is equal to 0. Mu 0 is not equal to 0. It implies that this sigma qm, that is the net magnetic charge enclosed by the Gaussian surface, that is equal to 0. So what this suggests? This suggests this thing, monopole does not exist in the nature. Because when we think about the summation of the magnetic charges, it implies that north pole that we consider as the positive magnetic charge, south pole that we consider as negative magnetic charge. So when sigma qm, that is 0, means single independent pole is not available in the nature. So this one is the proof of that thing. Monopole does not exist in the nature. Clear to all of you up to this one? Now, example 5.6. Many of the diagrams given in figure show magnetic field lines wrongly. Point out what is wrong with them. Some of them may describe electrostatic field lines correctly. Point out which one. Okay. So see this particular figure 1. So magnetic field lines are not like coming out from a single point for the current carrying conductor and are perpendicular to the conductor and straight lines. So first one, that is a wrong one. Second one, so field lines are represented in this figure B, are also wrong one. Why? Because we know this thing, magnetic field lines never intersect each other. Never intersect each other. So this is second one, that is also wrong one. Then this one is toroid, and magnetic field lines are represented here in the circular loop form, and all the field lines represented here are parallel to axis of the toroid. So this one is correct one. Then figure D. So this one is the solenoid, and at the end of solenoid, the field lines given to you are straight lines. It implies that here if we consider any closed surface, then we will get some net flux passing through it, which is never possible. So at the ends, the field lines are always curved one, because field lines always form a closed loop. So this D, that is also wrong one. Then E. Yes, E represents the magnetic field lines of short bar magnet. So that is correct one. Then F. So in figure F, say from this upper plate, the magnetic field lines are coming out. Then field lines enter to this lower plate. And then from lower plate, it is not coming out. It implies that figure F is not representing the magnetic field lines. But see, from upper plate it is coming out and it entered to the lower plate. It implies that these particular field lines are electric field lines which comes out from the positively charged plate to the negatively and enter to the negatively charged plate. So we can say this one is the figure of electric field lines. Figure G, in which the magnetic field lines are represented here north to south, but again are perfect straight lines parallel to each other. So it is not possible here between two poles the uniform magnetic field is there. So this G, that is also wrong one. Clear to all of you? Now example 5.7. Question A. Magnetic field lines show the direction at every point along which a small magnetized needle aligns at the point. Do the magnetic field lines also represent the line of force on a moving charge particle at every point? No. Because when we think about any moving charge in the magnetic field, then the force on it, that is given by the equation F, that is Q into V cross B, means the force is always perpendicular to the magnetic field. So field line, or we can say the direction of the magnetic field, in that particular direction charge will not experience the force, and therefore we can't represent the magnetic field lines as line of force. But in electric field lines, we represent electric field lines as a line of force, because when any charge Q is placed in the electric field, the force act, that is Q into E. So the force that is in the direction of the field. Therefore, you can represent it as a line of force also, but in magnetic field it is not possible. Clear to all of you? Question B. Magnetic field lines can be entirely confined within the core of a toroid, but not within a straight solenoid. Why? Because toroid, that is endless. Okay. So field lines can be confined within it. But for the straight solenoid, from the end of the solenoid, when field line come out, then it will form a closed loop. So inside it, we can't confine it. Okay. Now question C. If magnetic monopoles existed, how could the Gauss's law of magnetism be modified? So if monopole exists in the nature, then on the right hand side of the Gauss's law, we have to write mu0 into Qm. So integration B dot ds over the closed surface, that is equal to mu0 into Qm. In this way, we have to modify it, and we already discussed this thing in the theory also. Question D. Does a bar magnet exert a torque on itself due to its own field? No, it is not possible. Does one element of a current carrying wire exert a force on the other element of the same wire? Yes, it is possible if the current carrying wire is not a straight wire. If it is a loop, or if it is in any other shape, then definitely one current element exerts the force on other current element. Clear to all of you? Next, a magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is zero? Yes. If net charge that is zero, then also it may have the magnetic moment, because magnetic moment arises that is due to current loops, and current loops are formed due to motion of charges. So if net charge of the system that is zero, but the motion of charges can produce the magnetic moment. Clear to all of you? Now the next topic, that is the Earth's magnetism. Now see, Earth itself behave as a magnet, and Earth have its own magnetic field. Okay. Now at the surface of the Earth, the magnetic field that is of the order of 10 raised to minus 5 Tesla. Now, why this magnetic field of Earth is there? Okay. So the reason behind this one, that is the magnetic field arises due to electrical current produced by the convection motion of the metallic fluid at the core of the Earth. Okay. And this particular effect that is known as dynamo effect, and due to it the magnetic field of Earth presents. Clear to all of you? Now the magnetic field lines of the Earth resembles that of a magnetic dipole located at the center of the Earth. And this one is hypothetical one. Okay. The axis of the dipole does not coincide with the axis of the rotation of the Earth, but is presently tilted by approximately 11.3 degree with respect to the latter. In this way of looking at it, the magnetic poles are located where the magnetic lines due to dipole enter or leave the Earth. The location of the north magnetic pole is at latitude of 79.74 degree north and a longitude of 71.8 degree west, a place somewhere in North Canada. The magnetic south pole is at 79.74 degree south and 108.22 degree east in Antarctica. Clear? Now the pole near the geographic north pole of the Earth, that is called the north magnetic pole. Likewise, the pole near the geographic south pole, that is called the south magnetic pole. There is some confusion in the nomenclature of poles. If one looks at the magnetic field lines of the Earth, one sees that unlike in the case of a bar magnet, the field lines go into the Earth at the north magnetic pole and come out from the south magnetic pole. The convention arose because the magnetic north was the direction to which the north pole of the magnetic needle pointed. The north pole of the magnet was so named as it was the north-seeking pole. Thus, in reality, the north magnetic pole behave like the south pole of a bar magnet inside the Earth and vice versa. Clear? Now, to avoid this confusion given to you in this paragraph, simply we have to follow the regular sign conventions. For any magnetic dipole or for any magnet or for any system which behave as a magnet, the field lines always comes out from North Pole. So the point from where the magnetic field lines of Earth are coming out, simply say that is magnetic north. And the magnetic field line of the Earth enter to the point, so say that is the magnetic south. So in short, we can say the direction in which geographic north of Earth is there is the magnetic south. And in the direction of geographic south, there is the magnetic north. And you can justify this one also like this. When we place any magnet in the Earth's magnetic field, then north pole of that particular bar magnet always align towards the geographic north, and magnetic south pole of that bar magnet always align towards geographic south pole. Now we know this thing. The unlike poles attract each other. So if we imagine the Earth as a magnet, so suppose this one is the magnetic moment of Earth, or we can say we consider Earth as a magnet. Now above it, if bar magnet is there and this one is the north pole of the bar magnet, it implies that this should be what? The south pole of the Earth, because north south attract each other. And if the south of the means magnetic south pole of the bar magnet is aligned in the geographic south direction, it implies that this particular the one that is north pole of the Earth, because north attract south and south attract north. So without confusion, simply you can represent this thing in this way. Clear to all of you now? This particular second figure, that is just for understanding, to avoid this particular confusion, or in other words, we can say to make clear our mind. In exam, you have to write only up to this one as per given to you in the text. Clear? Now example 5.8. The Earth's magnetic field at the equator is approximately 0.4 Gauss. Estimate the Earth's dipole moment. Clear? Now the solution of this one. See, the Earth's magnetic field that is given to you 0.4 Gauss. So we can write that is 0.4 into 10 raised to minus 4 Tesla, or we can say that is 4 into 10 raised to minus 5 Tesla. Now, B at equator. So we can write the equation for B at equator, that is mu 0 upon 4 pi m upon r cube. Now we want to calculate Earth's dipole moment. So we have to make m as a subject of equation. So substitute all the values given to you. B, that is 4 into 10 raised to minus 5. Mu 0 upon 4 pi, that is 10 raised to minus 7. M as it is that we want to find. And r cube. So at equator, at the surface of the Earth, the distance of the point that we can take as the radius of the Earth. So that is 6.4 into 10 raised to 6 and cube of it. So make m as a subject of equation, and then after solve this one, you will get the magnetic dipole moment of Earth. Now, next topic, that is magnetic declination and deep. See, actually, magnetic field of Earth, that is not constant at each and every position on the surface of the Earth, right? It is different one at different positions. So suppose you want to take idea about the magnetic field of Earth at any particular position at the surface of the Earth, then we have to think about some parameters of Earth's magnetic field. One, that is magnetic declination, magnetic deep angle, or we can say another one, that is inclination, then horizontal component of Earth's magnetic field, vertical component of Earth's magnetic field. And if we find out all these things, then we will get the perfect idea about the direction, magnitude of Earth's magnetic field at a particular position. Now, first of all, we have to discuss magnetic declination and deep, these parameters for the Earth's magnetic field. Say, first of all, we have to understand the geographic meridian and magnetic meridian. Geographic meridian means what? The vertical plane containing the longitude circle and the axis of rotation of the Earth, that is called the geographic meridian. Then magnetic meridian is a place, is the vertical plane which passes through the imaginary line joining the magnetic north and the south poles. Clear the idea? A magnetic needle which is free to swing horizontally would then lie in the magnetic meridian, and the north pole of the needle would point towards the magnetic north pole. Now, the angle between the true geographic north and the north shown by the compass needle is called the magnetic declination or simply declination, as shown in this figure. See, this particular line that is representing the true geographic north-south. And when we place the magnetic needle here, then suppose magnetic needle aligns in this particular direction. So the direction which is represented by north pole of the magnetic needle and the direction represented by the south pole of the magnetic needle. So we can say this particular line, that is the magnetic axis. So the angle between these two axes, one geographic axis, another one that is magnetic axis, that is called magnetic declination or simply declination at the place where the magnetic needle is placed. Clear to all of you? If magnetic needle is perfectly balanced about a horizontal axis so that it can swing in a plane of the magnetic meridian, the needle would make an angle with the horizontal, that is known as the angle of deep, that is also known as inclination. Suppose at any place, at this particular place, we place the magnetic needle, right? So magnetic needle always align in the magnetic meridian. Magnetic meridian, that is the plane passing through the magnetic field line passing through this particular place and the magnetic axis. Okay, so needle always align in the plane, that is the magnetic meridian. Okay, but when you place this magnetic needle at this particular position or at this particular place, then no doubt it is in the magnetic meridian, but it will not be aligned perfectly horizontal at each and every place. Suppose it is in the magnetic meridian, but it align with the Earth's magnetic field at this place, not perfectly horizontal, but slightly like this. So when your magnetic needle align in this direction, it implies that at this particular place, the magnetic field that is in this direction. So here, now if we imagine the horizontal direction, so horizontal direction at this particular place is like this. So angle made by Earth's magnetic field at this position with respect to the horizontal direction, ani and ani vachcheno angle, that is called angle of deep. Now clear the idea? Now angle of deep, that is clear, and it is also known as inclination. Now see, suppose here as shown in this figure, this particular plane represented by red rectangle, that is the magnetic meridian. That is the magnetic meridian. Now, suppose at this particular place, the magnetic needle is placed, and your magnetic needle align in this particular direction. So we can say at this particular place or the position, the direction of Earth's magnetic field, that is this BE. Now, this one is the horizontal direction. This one is the vertical direction. So angle made by this magnetic field of Earth with respect to this horizontal direction means this angle I, that is the angle of deep or inclination. Clear to all of you? Now, if we take cos I, then cos I, that is adjacent upon hypotenuse, so that is HE upon BE. So we can write the horizontal component of Earth's magnetic field, that is BE cos I. If we take sine I of this angle, then sine I, that is opposite, means ZE upon BE. ZE, that is the vertical component of Earth's magnetic field. So if we know Earth's magnetic field at a particular position at the surface of the Earth, then with the help of inclination of Earth's magnetic field at that position, we can calculate the horizontal and vertical components of Earth's magnetic field. If we have horizontal and vertical component of Earth's magnetic field at any place, then we can easily calculate the magnetic field of the earth at that particular place, as well as we can find the direction of earth's magnetic field at that particular place. Clear to all of you? Now example 5.9. In the magnetic meridian of a certain place, the horizontal component of the earth's magnetic field is 0.26 Gauss and the deep angle is 60 degree. What is the magnetic field of the earth at this location? Now, HE that is given to you, horizontal component of earth's magnetic field 0.26 Gauss. And deep angle is 60 degree. So HE that is 0.26 Gauss, that is 0.26 into 10 raised to minus 4 Tesla. I that is equal to 60 degree. What is BE? So cos I that is HE upon BE, we discussed in the theory. So BE that is HE upon cos I, HE that is 0.26 into 10 raised to minus 4 upon cos I that is cos 60. Now solve this one, you will get the answer. Clear to all of you?